All right, so kinetics is the study of the rate of reactions, and this is the part of the reaction diagram that is above the energy of the reactant. And so you can see here, this is kind of the part of the energy diagram that corresponds to kinetics. So the height, the maximum height of that bump on the reaction diagram, that is the activation energy, and the larger that value is, the higher that hill, the slower the reaction. And so you might remember the bicycle analogy, that it just takes a really long time the higher the hill is to get up over that hill, and it takes more energy. So the transition state is that species that is at the highest point here. It is transitional. We're never going to actually see it, but we have to be able to assume that it's there because we get to the intermediate or product further on down the line. And often those transition states will have partially broken bonds. You'll see those as dashes, or like complexes between multiple molecules. So the idea of kinetics and also of mechanisms and how reactions occur is that molecules actually have to collide with each other. And so I'm going to switch over to a simulation here. All right, let's start. Let me get that so you can actually see it. There it is. All right, this is a PhET simulation. And currently this reaction box is empty, and we have a reaction where the equilibrium constant is 1. In other words, delta G is 0 between the reactants and products. That's the thermodynamic description. But the kinetic description, you can see that it has this activation energy in the middle. So let's put some of A in here. And since A actually has to react with B and C, of course, if we don't have B and C, the VC molecule, then no reaction is going to occur. One way I could make reaction occur, or at least collisions occur, is to add B and the BC molecule. So now that's bouncing around in there. And there's a good number of collisions, but I'm not getting any product. And if we look at our energy diagram, we can see that the kinetic energy is really low, or the average energy is really low compared to the height of the activation energy. And so we need to give this reaction a little bit of energy in order to actually have the reaction occur. So we do that by increasing the temperature, by heating it up. You can see that raises the average energy. The molecules are bouncing around, they collide more. And so at that point, we actually start to get some of the product. And it might take a little bit, since the delta G here is 0 and the equilibrium constant is 1, at equilibrium, we would expect to get equal amounts of the reactants and the products. All right, so let's return to our PowerPoint. Okay, so the nature of reactants, like how percentage of the reactants will lead to productive collisions when they collide, will actually react. That's important for the rate of the reaction. The concentration of reactants, like we just saw, is important. Temperature, and then catalysts, which can be added to reactions to lower the activation energy, so that the reactions happen more quickly. So when we look at organic reactions, we'll look at the rate law. Okay, and this is the relationship between the reaction rate and the concentration of reactants. It is experimentally determined. And you can see high activation energy corresponds to low rate constant. Okay, so the rate equation tells us about the mechanism of the reaction. And this is really what we're going to lead with when we go on to the next chapter and start looking at substitution reactions. And so here, and actually we'll look at it a little bit on Wednesday as well. The idea is that a rate equation, you can see here, it contains all of the reactants in a one-step mechanism. And so you can kind of think about the reverse too. Let's say you measured this rate equation. That means that you have a one-step mechanism. Okay, and I mean the underlying and general idea here is that a rate equation contains all of the concentration terms involved in the rate determining step in a multi-step reaction. And so if you know that you have A, B, and C as your two reactants, but only AB is in the rate equation, then there has to be something happening in the rate determining step that doesn't involve C. And so if you measured this rate equation, but you know you put A, B, and C together, then this must be at least a two-step mechanism, because that first step just involves, the rate determining step just involves AB, according to this. But somehow C has to be involved. It just must happen in some non-rate determining mechanistic step. And so here's another version of what that would look like. If you measured a rate equation like the one shown here, then at least you have two steps to your reaction. And so your reaction coordinate diagram would look like this. And in that first step, you have the rate determining step. It has the highest activation energy. And in that step, only A and B are involved and their bonds break. A second step, now that one involves C, but it's not the rate determining step. It has a lower activation energy. So in this way, we can connect our rate equations, which we measure, to a proposal of a mechanism. And reaction mechanisms are really fundamental to organic chemistry, and we use lots of different ways of probing how they happen, how the starting material turns into the product. And that's a lot of what we're going to be looking at in class in the next couple of weeks.